So, hello everyone, and thank you very much for inviting me to give this seminar. As I said, I would be extremely happy to be there in person, and let's hope it's going to happen soon.
Yes.
But today, via Zoom, I'll talk about quantum complexity in the Krylov basis. And okay. So outline of my talk is as follows. I'll give some brief introduction and motivation. Then I'll go to the main part of defining Krylov basis and how we can use it as a definition of complexity for states and operators. And then I'll show some explicit examples that will hopefully illustrate the idea and give you some feeling of how it could work. And then I'll conclude and pose some open questions. So my talk will be based on two papers. This one with the group at University of Pennsylvania with Vijay, Javier Magan, and also student of Vijay, Austin. And the second paper is with Javier and also my student here in Warsaw, Dimitris Patramanis. So please stop me at any point. I was told that there should be many questions. So if you have comments or questions, I'll be very happy to stop and discuss. And since this topic is relatively new and recent, probably there's like still many open things and that we don't really understand, or we should still understand better and explore better. So any question is welcome at this point, and is definitely very valuable. Okay, so maybe just a general introduction to and motivation of why are we doing this. So first, as I'm sure you all know, that this entanglement and quantum information revolution, because I think by now we can call it revolution in ADS-CFT, that started with these works by Ryu and Takayanagi, changed our perspective on holography and quantum black holes. And one of the reasons why this was so useful, mostly on the technical level, I should say, but then it turned out to like infiltrate to basically all the parts of holography, is that these tools like entanglement and some of the quantum information tools that we were able to use in ADS-CFT, they have a very good definition, let's say in terms of some powers of a density matrix and so on, that we can use define either using replica trick or some parts of like that. Is there some talk? Sorry, is there some question?
Actually, you are not muted.
Okay. But as I'm going to motivate in a moment, recently, and I'm sure many of you know this, that recently there's a demand for some more fine-grained tools that would probe late-time dynamics of ADS-CFT that we vaguely call, in this quotation mark, complexity. And I'm going to explain to you what type of notions we have in mind when we talk about this complexity. And the question of my talk and somehow this area of research is whether there's a good universal definition of complexity, similarly to this replica tricks, or maybe some notion that we could apply in quantum field theories, and in particular in ADS-CFT. So basically, that's where we are hopefully going and what we would like to develop. But before I go there, let me just remind you, why do we actually want or need these notions of complexity in ADS-CFT? And so there are canonical examples where actually this popped up. And one of the most famous that you see in most of the talks is basically this observation due to Lenny, that when we study the time-evolved thermophile double state, a la Hartmann and Maldacena, so basically we take a thermophile double, some maximally entangled state of two CFTs, let's say, and then we do the non-trivial time evolution, say with a sum of the left and right Hamiltonian, or maybe only with left or only with right. Then the dual geometry has interesting properties, namely, so of course, this dual geometry is this to the thermophile double is this Penrose diagram of eternal black hole. And then when we study these quantum information tools, like for example, entanglement entropy between two intervals on both sides, then this entanglement entropy saturates after some relatively short time of order the size of the interval. But somehow there are still properties of this time-evolved black hole. Namely, basically, there are still some slices that go into the behind the horizon of the black hole that continue growing with time, already after this very short time of saturation of entanglement. So basically, in this program of space-time from entanglement, we somehow face a small problem that even though we know entanglement entropy, or some quantum information measure that probe this geometry in the way we understand, there's still some property of the geometry that keeps growing, and we cannot probe it just with entanglement. So Lenny was really puzzled by this, and he posed these nice questions like, what is the CFT dual of this growth of the Einstein-Rosen bridge with time? And he proposed that there should be some notion of complexity, maybe a circuit complexity or something that can probe this state in a meaningful way for much later times than this entanglement entropy. And maybe that could be a dual of this growth of the Einstein-Rosen bridge. And I'm sure probably many of you know, like this sparked also another kind of avalanche of developments on both sides of holographic complexity and the notions of the complexity in field theories that could actually make this statements qualitative. So that was the first motivation why this complexity would be needed, basically for studying, for understanding better this late time evolution of the thermofield doubles. Okay, the second point where the notions of complexity showed up was basically this subject of operator growth, or measuring the size of operators. And also this dates back to works actually in the past, but it was very sharply stated in this paper by Schenker and Stanford, and also follow-ups by Roberts and Stanford and also Lenny, that when we take again some thermofield double state, for example, and then we perturb it by some light operator at some time in the past, for sufficiently late times in the past, this small perturbation to the state can be actually tragic for the entanglement in the state, and can completely destroy the entanglement between the left and the right of this purification. And so this was called the butterfly effect. And people also tried to understand how could we actually measure the size of the operator, or the impact of this operator on the entanglement in the state. And it was maybe more generally formulated in the language of these precursors, that we take some operator W that is independent on time, we sandwich it with between the unitaries. So we get some really time-dependent operator, and we would like to have a universal good notion of the operator size as time evolves, or somehow people also refer to as operator complexity. That would tell us how difficult or how complicated this operator is as the time grows. And some partial answer to this has been given, and they led to a lot of progress. Namely, people have computed out of time order correlators. And you can think about them as measures of the size of this operator of t, in a sense that at the initial times, this correlator basically factorizes into 1. But then once we start doing this non-trivial evolution, say in some chaotic systems that describe black holes, then the size of the operator shows up in a certain behavior of the out of time order correlators, that basically it deviates from this 1 in an exponentially fast way. And that led to this basically Malda-Schenker-Stanford bound on chaos in holographic CFTs. But still, like this, let's say in some sense, this notion of the size or operator complexity in out of time order correlators that has not been very explicit and sharp, in a sense that we would maybe like to understand from the language of complexity.
Sorry, and Pawel, can you even intuitively say, can you even intuitively say why this exponential is related to the size? I didn't get that. Sorry.
Okay, I hope I will make some more statements on that at the end. If you can wait with me, that would be great.
Yeah.
Okay. Okay. So basically,
Sorry, Pawel.
yes.
Sorry, I have one more question. Again, you can choose not to address it or later, which is, the original ideas of scrambling, for example, in Preskill and Hayden, actually had to do with how entanglement spreads rather than operator spreads or OTOCs. And is it clear that the two notions are the same? That if you actually measure how entanglement spreads, and the rate will be correlated with how the OTOC grows? I've not been able to convince myself, but I wanted to ask.
I'm not 100% sure if these two notions are the same.
Okay.
In fact, I think there are some like counter examples where you can take some large n limit and you see that, for example, entanglement spreads in a much faster way as you would expect in the large n theories, but out of time order correlators behave the same way as in some rational theories.
I see.
So,
I see. Okay, I'll ask you for that later then, offline. Thank you.
Yes. Okay, but again, as I want to stress, these developments and these ideas are relatively fresh, and we still don't have a very sharp and good definition of what this complexity should be. There are many proposals, especially, of course, when I mean the good idea on the field theory side, especially what this quantity should be microscopically. And there are several ideas, and basically you could group them into two parts. One that would that attempt to define some complexity for states, like sometimes called complexity of formation or complexity of certain evolution by unitary operators. And there you can find, for example, geometric approaches a la Nielsen, where you would try to define a complexity as some abstract is a geodesic in some abstract space of unitaries on which you put a metric and so on. I will not talk much about it. There are some more field theory-based definitions where you try to define complexity based on path integrals using something like ideas from ADS tensor networks. I will also not talk about it. But generally, what we would like to have is some very good and sensitive distance measures between states that will tell us that will allow us to distinguish states for very long times and in a kind of fine manner, and hopefully we'll be able to reproduce that somehow in these properties of the late time thermofield doubles. On the other hand, so basically the hope is that once we understand this complexity of states, we're gonna be able to understand this growth of Einstein-Rosen bridge or late time physics of black holes, and hopefully maybe even singularity and so on. On the other hand, when we talk about this complexity of operators, we can actually have the second group when we talk about complexity of operators associated to the growth, maybe somehow chaotic nature of your model and so on. There are some explicit, so basically there we talk about this operator size or operator complexity, and we would like to have a sharp notion there. So there are some models, like for example in SYK, where we can define this operator size in terms of some kind of like a number operators in terms of fermions. There are some attempts to define this complexity by some momentum of a particle in ADS that would be dual to some local excitations. This was done, for example, in the work by Maldacena, Lin, and Zhao. And as I said, there are these works on out-of-time order correlators that we still we know that they could be good probes of how operators spreads, but still we don't fully understand how they are related, how we could link them to some notion of complexity that we know maybe from quantum complexity theory. But the hope is that if we understand this complexity of operators, then actually they will be more related to some near horizon physics of black holes, maybe some scattering at the vicinity of the black holes, or maybe like in these works as some symmetry, they could be related to some symmetries in the near horizon region and so on. But again, this is still under like very active development, and we only uncovered some small pieces of all these games, and we still don't even, and we would like to hopefully understand eventually how these two notions for operators and states are linked with each other, if at all. Okay, so that's basically my general, and I apologize, by roughly vague motivation. And in this talk, I'm going to discuss a notion or some notions of complexity based on the so-called Krylov basis, and that can be universally defined and computed in systems from quantum mechanics to quantum field theories. And then I will present some of the recent results for both. So I'll show you that these notions based on Krylov complexity, this can actually be applied to both of my motivations, to the growth of the thermofield double and to defining the size or the growth of the operators. And maybe the spoiler or like a take-home message that I would like you to take, and hopefully this spoiler will become clearer by the end of the talk, is that basically I'll be defining some notion when I will be talking about some state or the operator. I'll be able to expand it in this Krylov basis, and the coefficients in this Krylov basis will be able to provide us some probability distribution for this operator or the state, and then based on that probability distribution, I'll be able to define the growth of operator or complexity of states and so on. If this is not clear at this step, if you have not heard the story at all, that's great, and hopefully by the end of my talk, this will become clear. And this is, as I said, this will be based on this talk with Vijay and Javier and Austin. But actually, there has been some very nice later works, starting from this paper by Berkeley group in 2019, where they tried to use these notions of Krylov basis and Krylov complexity to define the growth of operators. So I'm not going to put too many references in the remaining parts, but these are basically the main ones for the growth of operators. Okay, so is at least the motivation clear? And are there any questions at this point? Okay.
So, sorry, just to say, this seems like more of a notion in state space or something, rather than operator, is it? That is, you expand in a, anyway, you'll explain, but you choose this particular basis and you ask how complicated it is to express a given state in that basis.
Yes. So in my talk, I'll be talking about the state definition, but I will show you that actually to define the growth of the operator, we also need to introduce a norm in the space of operators that effectively defines for you a state associated to that operator.
I see.
But your intuition is correct. It indeed, like it's more natural definition for states, but it works for operators in a nice way, as was done by this.
I see. Thank you.
Okay. So before I go to definitions, let me maybe describe this idea of Krylov basis. And probably some of you remember it from some algebra or maybe computer science, but if not, let me just briefly review it because it's relatively simple concept. Okay, so generally, let's consider some unitary evolution, or you can actually think about it as some quantum circuit where we start from some initial state psi0, and then we apply it to some unitary evolution e to the minus iht, where this h can be your physical Hamiltonian, but does not need to be. It might be some circuit Hamiltonian or whatever. And again, t might be your real time, but again, it might be some circuit time that you will. And as you know, we can formally write this unitary acting on this initial state as some sum from n equals to 0 to infinity, this power series in t. And then all these powers of all this set of states psi n that we formally define as basically the subspace of the state psi0 and all the possible powers of the Hamiltonian acting on this initial state. So we have psi0, psi1 is just Hamiltonian acting on psi0 and so on. So we have this, this is called, sometimes referred to as this Krylov subspace, where we start from some vector, we take a matrix, and we apply all the possible powers of this matrix on this initial vector. Okay, and of course, in most of the examples, this is not the basis because actually, probably always, this is not the basis because these states are simply not orthogonal. So the goal is actually, given that this Krylov basis, given that this Krylov subspace, we would like to construct an orthonormal basis, and that I denote as Kn, this will be the Krylov basis, and extract and expand this state, the unitary acting on this initial state, in this Krylov basis. And it turns out that we can do it recursively. And this recursive algorithm is called the Lanczos algorithm, and it works as follows. It basically takes this Krylov subspace with this psi0 and all the possible powers and applies some Gram-Schmidt like orthogonalization step by step. So we do it recursively in a sense that we first start with some state a n plus 1. So of course, actually, the first state is always this k0 in the Krylov basis. That's the initial state, psi0. Okay. Then we do this definition recursively in a sense that we define the state a n plus 1, where we act with the Hamiltonian on the vector kn, and we subtract two coefficients, ans and times kn minus bn times kn minus 1. And then once we construct the state an, then we actually, it's not normalized. Then we define the normalized Krylov basis eigenvector kn as basically this an divided by bn, where this bn is simply the normalization of this vector an plus 1, and an is the expectation value of the Hamiltonian in the state kn. It's actually a nice exercise if you do it step by step, starting from the first one, psi0, and then age. You see that what you are doing is nothing but you're starting with your initial state, hitting with the Hamiltonian and make sure it's orthogonal to the previous vector, then normalize it, then hit it again, and then subtract it, make sure that it's orthogonal to the previous two, and so on. So this is what this Lanczos algorithm does for you. And actually, a nice and important part of this algorithm is that it gives you these two sets of coefficients, ans and bns, on top of course, this important Krylov basis. And they will be very important in the rest of my talk. And they even have their name, namely Lanczos coefficients. And we choose them such that...
Is this algorithm any different from the Gram-Schmidt procedure?
Excuse me?
Is it any different from the Gram-Schmidt?
Yeah, sorry, thank you. I mentioned that this is like Gram-Schmidt procedure for this Krylov subspace. Thank you.
Okay.
So, Pawel, one question. So, it could happen that at a particular stage you may get a new vector, which is linear, which is not a linearly independent one compared to the previous ones. Then what does one do?
Exactly, and then this is a very good point. So then your procedure stops, right? Notice that what I'm talking about here and what I'm describing is like as general as it can be. So it can work for some simple integrable models or like harmonic oscillators and so on. So when you consider some simple or trivial dynamics, for example, if this is some eigenstate of this Hamiltonian, then you will only have this one Krylov basis vector or two Krylov basis vectors in some very simple models, and there will not be any complicated complex dynamics for your system. But as I will show you in some generic examples that we are interested in, this Krylov basis can be even infinite dimensional and so on.
No, I mean, it could happen that at some point you need to stop, and
yes.
The next die you have to start with a seed as the next die.
Excuse me?
I mean, the psi n may be linear combinations of the previous n minus 1, but psi n plus 1 may not be. May have a new component. In that case, is it that you start with that psi n plus 1 as a seed vector again, and then go on creating the basis?
Sorry, I'm not sure if I understood. If psi n will have a new component?
I mean, I'm saying at psi n could be linearly dependent.
Yes.
With respect to the previous n minus 1 vectors.
Of course,
In that case, you will not get a new basis element. But but psi n plus 1 could be linearly independent now, right? So you start with that again, right? Then you...
Well, in general, they're of course dependent, and then the point is like by apply, like you basically apply a next power of Hamiltonian, and then you try to construct a new orthonormal or orthogonal state to everything before, right?
Yeah.
And that's not always possible if you have some trivial dynamics, for example, or your model is very simple and so on.
Yeah,
So,
no, I mean, not necessarily only in the trivial case, but I mean, even in the non-trivial case, it might happen coincidentally that one of them suddenly turns out to be linearly dependent and then the rest are not. So you have to kind of continue. That could happen, right? And then the prescription for constructing it is just continue it.
Yeah, I assume that I guess it could happen. I don't know any explicit examples of that, but
Can I say something?
Sorry, Abhijit, what do you mean by just continue? I mean, once you get some linearly independent thing, then every further action of H will stay within that earlier subset, I thought. So continuing won't take you further.
I see. So you will just get a finite dimensional subspace.
yes, exactly.
I see. Okay, thank you.
Like
Okay.
sorry, but in particular, if you started with an energy eigenstate, right? Then you
Yes.
you don't go any further. Yeah.
Exactly. So in some sense, this basis it will be nice in kind of measuring for you how complicated your state is becoming, counting these numbers of your Hamiltonian in the moment. And again, for this algorithm to work in a usual way, we as I said, we define this K0 to be your initial state, and then for this to work for any n, this B0 is just 0 in this algorithm, and you can go with it. Okay, so basically by this definition, you can just reshuffle these terms here and then take this definition of an as a bn times kn to convince yourself that actually in this particular basis, your Hamiltonian becomes tridiagonal. Okay. By the way, and as you all know, like there's this famous saying that one generation trashes another generation treasures. So this is not by any means unexplored subject in many body physics and so on. And there are even books from the 1963 that describe this basically exact diagonalization or application of this Krylov basis methods to many body systems, or basically doing evolution with this tridiagonal Hamiltonian. And this is this famous book by Vishwanath and Miller. And okay, so as I said, in this Krylov basis, you construct it such that your Hamiltonian is not diagonal, but it's tridiagonal. And you can see this comes from this Lanczos algorithm and this action here, as I mentioned. So in other words, when you compute matrix elements, you have these Lanczos coefficients ANs on the diagonal. Then of the diagonal, you have B1, B2, B3, and so on, BNs, and then everything else is 0. Also in the literature, you always call this form of the Hamiltonian a Heisenberg form, and this will be actually very useful a little bit later. We'll be applying it to some random matrices where actually there are very stable and interesting algorithms, or like efficient algorithms to produce for you this Heisenberg form for any given matrix. Okay, so as I said, once you construct this Krylov basis, what we want to do is starting from this initial state e to the minus iht on psi 0, we want to expand this state in the Krylov basis kn, and we have some coefficients phi n of t in this Krylov basis. And by unitarity, of course, the sum of these coefficients is the sum of the probabilities, and they sum up to 1, right? So this phi n's in this states. Absolute values, they are just 1. And
sorry to interrupt, Pawel, please excuse me. Is it true that a general Hermitian matrix can always be written in this tridiagonal form, just as independent of Krylov? Is that generally true?
Yes.
Okay.
Yes.
Thank you.
Yeah, you can always bring it into this tridiagonal form by some appropriate rotation.
Okay.
Can I ask a question?
Yes, please.
Yes. This expansion you have for the general state psi of t in terms of the Krylov basis, does it not assume that your Krylov, your Krylov space is actually all of the Hilbert space? It's not a subspace, because you're using these vectors to expand a general state when you write psi of t as phi n t kn. So kn is an orthonormal basis, but in general, it's a subspace, right? It's not the full Hilbert space.
It is a subspace. That's right.
So a general state of a Hilbert space would not be expandable in general in terms of the Krylov basis, right?
Well, so at least when I'm just in this state, I'm not taking anything like outside this psi 0 and the powers of the Hamiltonian, right? Like
yeah, so that step I understand, but the second equality that you have, where you have written an expansion in terms of an orthonormal basis. So,
yes, but it's not any basis. It's just the basis of build of the orthonormalizing the powers of this H here in the middle on psi 0. So I'm not introducing any other operator of your theory, let's say, acting on psi 0.
I see. So if your Hilbert space is of dimension D and your Krylov subspace is dimension less than
usually
that,
lower.
still you can always do this expansion.
For this state, this I can always do, but not I cannot expand arbitrary state, as you're saying, in the Hilbert space in the Hilbert space, but in the Krylov basis, it's usually lower dimensional. Or at max it can be as many dimensions as Hilbert space, but it's a subspace.
I see. The same statement is also true. You haven't talked about it yet, but for operator complexity, when you define, so the same statement is true there also?
Yes. I will show you in a moment.
Okay, thank you.
Thanks for this question. That's very important. So again, let me maybe stress this. This was a good question to stress it. This Krylov basis or Krylov subspace, it depends on the state psi 0 and your H that you are using in this evolution. Okay, so it just takes all the powers of H on psi 0, but does not involve any other operations, let's say, and that's very important. So it depends on these two things here. As I said, this is some formal expansion of the state in this Krylov basis, and the important thing will be played by this probability distribution or this coefficients phi n's, probability amplitudes in the Krylov basis. And actually, by definition, again, of this Hamiltonian being tridiagonal in this basis and the definition of states, you can just hit this psi of t with I times time derivative, and you can use this definition of the Hamiltonian in the Krylov basis, and by reshuffling the indices, you can show that these coefficients simply satisfy this discrete Schrödinger equation, where, again, these ANs are this diagonal pieces, and BN, the Lanczos coefficients BNs, they move you off the diagonal in this Krylov basis as before. So,
sorry, Pawel, suppose your basis ends at the nth guy.
Yes.
H acting on the nth guy takes you into some general linear combination of all the others.
Yes.
So this tridiagonal structure there breaks down, right?
Yes.
And this differential equation holds only up to that?
It will only go up to n when it's not diagonal. And
okay.
Up the last diagonal guy. Yes.
Okay. Thank you.
And the point. Yes.
So it seems like the dimension of the Krylov basis depends on how the initial state psi 0 is spread in terms of the energy eigenstates. Is it true? So is the complexity somehow related to the spread of initial eigenstate in terms of?
That's where I'm going. Thanks.
I mean, just to come back to what Shiraz said, does it break down or is it just that it closes? I mean, for example, if you started with K0 being an eigenstate, then it just closes at K0 itself, and you conclude I d by dt phi 0 is A0 phi 0, which is correct.
Yeah, that one, that's true.
Information
needed
to, I mean, sorry, you should go on. There's no further information needed anyway to time develop the state, right?
No, but suppose it stops at the 10th guy. Then you would then it will have 10 coefficients, right?
Yes.
At that stage.
Exactly.
So the structure will no longer be true for the 10th guy.
Yes. And you will see that, for example, the coefficient in this equation in front of B10, let's say, or something, that B10 becomes 0.
Right, B10 would become 0, and then but you would have some coefficient for 1, some coefficient for 2, up to 9.
Yes.
But that will be enough to propagate the state psi 0 forever, right?
Correct. I'm just saying, but the structure of it being tridiagonal would not hold that. So the differential equation would not hold that.
Yes, absolutely. Sorry, I misunderstood.
Yes. Okay, so basically the point is that as I mentioned to you before, once we construct this Krylov basis, we have these orthonormal states, but we also have these Lanczos coefficients. And basically, once you have them for any, like for n up to you, whatever, then to determine this coefficient, you need to solve this Schrödinger equation, discrete Schrödinger equation. It's like some kind of hopping equation. That will become more precise in a moment, with this initial condition that this coefficient phi n at time t equal to 0 just projects you on this initial basis vector k0, that is this state psi0 that you started. Okay, so let's I mean, what I described to you up to now is like super general. You can apply it into any model you want, as long as you have some, you know, reasonable assumptions about some unitarity and some initial states, and sometimes you might get a trivial answer or an answer that terminates at some very quick, basically recursive order. But any what I just described for you now is like almost any dynamics in nature can be put into this kind of one-dimensional problem. But don't get tricked. Of course, there's no free lunch, in a sense that, you know, you can always map it like this, but generically these an and bn coefficients, they will be like monstrous, and you need to work with them numerically. So there's really no free lunch. But of course, I'm giving this talk for the reason that there are some examples where we can actually solve it either analytically, or we have some nice numerically tractable examples where we can study these coefficients and the states and so on. Okay, so there's a very important point that actually that goes into the logic behind this, namely. That these Lanczos coefficients that one needs to solve this Schrödinger equation, they are actually also encoded in the so-called return amplitude, or maybe for people that also that know it from many body systems, to so-called autocorrelator, or sometimes it goes under the name of Loch-Schmidt amplitude or Loch-Schmidt echo. Namely, we can consider this state at psi0. So this is this state that we started with, and project on this psi0 our state at time t. So this return amplitude is defined as basically an expectation value of e to the iht in this initial state. And by construction, actually, this return amplitude, because you know, we define this Krylov basic expansion of this state in this phi in this basis, such that this return amplitude becomes just a complex conjugate of the zero coefficient in the Krylov basis, right? So this is the psi0 is our k0, and the coefficient of k0 is psi0 of t. There's sometimes in the literature there's a convention that people do it other way around. So this is actually either psi0, or here I'm doing psi0 star, but because I choose to define it like this. And okay, so how can we extract these Lanczos coefficients from this? Namely, we can consider all the moments of this return amplitude of this autocorrelator, namely the derivatives of this autocorrelator at t equal to 0, nth of them. And they are, of course, given by the powers of e to the I h, this circuit Hamiltonian to the power 8, h, evaluated in this initial state, this k0 or psi0. These are, of course, by definition, the moments of this return amplitude. And if we know all the moments or of the theory, we can actually uniquely define, or we can extract from them these Lanczos coefficients. And again, there's like some nice computer science algorithm that tells you how they are related. I didn't mean to scare you with this picture. It's basically just some drawing that shows you like that counting certain paths on this graph tells you how do you find the relations between moment n and the Lanczos coefficients a0. So basically, you just plot, denote all the bottom nodes by moments, 0, 1, 2, 3, 4th moments, and basically counting all the paths, independent paths up to moment n, with the lines labeled by either bn's or an's, just gives you some polynomial relations between these Lanczos coefficients and the moments n of your model. So you can do it in a very efficient way if you know the moments of this return amplitude, and this will also be important. Okay, and then as I mentioned, actually one can apply the same ideas to the operator growth in the Krylov basis, and this was in fact already first done in this 2019. basically in that setup, we have the following question. We start with some Heisenberg evolution of an operator that is governed by the Seiberg equation. And of course, you know that the formal solution to this problem is that we can just write this initial operator at t equal to 0 as e to the iht, e to the minus iht. And again, that operator can be that formal solution of this evolution equation in any model given by Hamiltonian H can be written again as a formal power series in T. And now these operators, this is of course in the space of operators, these operators O and tilde that I denote here that appear in every power of T, they are defined by this nested commutator of your initial operator O0 with the Hamiltonian. So for example, this psi O0 is of course the initial Hamiltonian, O1 is the commutator of the Hamiltonian, O2 is the commutator of the Hamiltonian of the commutator of the Hamiltonian, and so on. Okay, and actually in that space of the operators, it is useful to represent it again by some kind of unitary superoperator. And basically that usually goes under the name of Liouvillean. So we define this Liouvillean superoperator as basically some operator that acts on whatever it acts by taking the commutator with the Hamiltonian. So this Liouvillean is basically taking your Hamiltonian and commuting with whatever it acted on. And this way, this operator at time t can be formally written as e to the I lt, this Liouvillean operator, acting on this initial operator O. Or in other words, these nested commutators, they are nicely written with this O and tilde are simply nth power of the Liouvillean on this initial operator. So again, we are faced in a similar problem. We are faced with a similar problem. Given this operator, we would like to expand it in some orthonormal. We would like to introduce some orthonormal basis that represents how this operator evolves with time. And a natural way to do it is again to start with this Krylov subspace in the space of operators. So basically we have this O, Liouvillean on O, two Liouvilleans on O, and nth power of Liouvillean on this initial operator. And we would like to construct or associate the basis vectors or basis elements with this particular structure. So how do you do that? Well, actually, first of all, in some sense, of course, there's a freedom in that in going from the space of operators to the space of states. But we must, in order to do this, we must pick an inner product, okay, in the space of operators. And so in a sense, we can define the states associated with these powers of the Liouvillean as long as we know when they are orthonormal or orthogonal and where they are not. And this inner product, there are several standard choices in the literature, but actually this discussion in this Berkeley paper and also actually back in the days in condensed matter literature was mostly done with this Whiteman inner product. So basically when I take some operator A and B or states associated with this operator operator A and some operator B, we will define their inner product between them as basically a thermal correlator of the operator B and operator A dagger, where the operator A dagger is moved on this by interval beta over 2 on this thermal circle. So in other words, this thermal correlator is the usual thermal correlator that you know, and then the operators are kind of dislocated along the thermal circle. Maybe for holography people, actually it's much easier to understand it. It's basically like taking a 2-point function on the opposite side of the thermophile double black hole, like eternal black hole, where one of the operators is on one CFT and the other operator will be on the other side, in the CFT on the other side of the black hole. Maybe by this, you will recognize also some formulas in the space of operators.
Sorry, and is one motivation for this to avoid short distance singularities for local operators?
Yes. Thank you. But again, there are some other nice choices in the literature, and people have tried to study like what is the dependence of the growth on the choice of inner product and so on, depending on the model. But that's also a nice topic. And but the most of the basically the point is that most of the inner products, so the things that I described before for the states were maybe more general, but most of the inner products for this operate in the space of operators, they will basically involve some sort of trace. So basically computing the trace in the thermal trace or in the vacuum or so on. And basically, because we'll be orthogonalizing, some operator state that corresponds to operator O, and then some state corresponding to the commutator of H with O, then actually in the trace this will vanish. When you compute the trace of Hamiltonian with commutator of the Hamiltonian with O. So by most of the choices in the literature for of the inner product, we actually can get rid of this Lanczos coefficients an in the whole procedure, but then we can just do the algorithm in the usual way as we did for the operators with a certain choice of the inner product. So maybe a good summary for this is that up to now, what I've been trying to explain to you is like how do you, given some state psi of t, that is some unitary acting on this initial state psi 0, we can expand this state with some coefficients phi n in the Krylov basis. That Krylov basis heavily depends on this initial state psi 0 and which h you are using. These coefficients phi n's, they are naturally giving you a probability distribution Pn, and they satisfy this discrete Schrödinger equation. And you can solve it by either doing the explicit orthonormalization and so on, but you can actually try to extract, you can start from the return amplitude, this S of t, and then extract from it directly this ANs and BNs, and you can just solve the Schrödinger equation to extract the PN. There are many shortcuts you can do to extract, if you're interested, as we will be in this probability distribution PN. On the other hand, for operators, you can, I'm not trying to argue that you have to choose some inner product, and then you can define some state. I write it like some O of t curly, that will be this e to the I LT acting on some state that corresponds to this initial operator. And again, in that choice of the inner product, you can expand this state with this. There's basically some, in the literature, there is some convention of putting I in front for the operators, but it's basically the same coefficients in this Krylov basis ON for the operators. And then you have a probability distribution, and then the Schrödinger equation without AN coefficients. And again, you can solve this by looking at the return amplitude, which will actually, this is again some convention in the literature that is usually denoted as some overlap between operator at 0 and operator of t. That is this initial coefficient phi 0 of t. And this will be, this actually, as for most of the choices of the operator, this will be basically some 2-point function, or depending, your operator that you study may be some complicated operator or even a commutator of operators, like in some cases like in OTOC. Then you will need to consider some maybe thermal, or depending on your inner product, some 2-point or higher point correlator of operators, and then extract the moments of this correlator, and then solve the Schrödinger equation to find these probabilities. So up to now, I just defined this Krylov basis and expansions, and there's, of course, for operators and for states, there are many connections. You can, for example, study some state psi of t that corresponds to some state psi 0, and then some operator on t acting on this initial state. Or, for example, if you choose this Weidmann inner product, if you want to study the growth of the operator in Weidmann inner product, actually you can mimic it in by the evolution or the spread of the state psi of t that has this form. So you, for example, start with thermofield double, and you will act with some operator t on moved a little bit on beta. But basically, if you do this, you're gonna get exactly the same return amplitude for this Weidmann inner product of of operators, and for these states, so the same ANs, the same BNs, no ANs, and the same probabilities. So in this way, like there's many ways of going between the growth of the state and the associated growth of the operator in your set. Okay. So are there any questions about this technical part? That was mostly. Okay, if not, let me finally define for you what I've been aiming at, namely this so-called Krylov or spread complexity. So given this expansion of your state or state associated to an operator in this Krylov basis, we, as you notice, we have to solve this discrete Schrödinger equation. And basically, by this, we are mapping the physics of the growth or the evolution or the spread of the state into a motion of a particle on the chain. So let's say this was of course this discrete Schrödinger equation, but the way it was defined originally is like if we even forget about these coefficients an, we can define a chain for that has all these nodes of the chain labeled by these coefficients phi 0. These are these coefficients of the operator in the Krylov basis. So we have the initial coefficients phi 0, the first one phi 1, phi 2, and so on, and then the links between those chains, or somehow like transition amplitudes between those links, they are labeled by these Lanczos coefficients b1, b2, b3, bn. And of course, these coefficients, as I showed you, they have this probabilistic interpretation. So their sum of their absolute values is 1. So this dynamics, the dynamics of the evolution that is mapped to this dynamics on the chain, it actually gives you a nice sense of a distance, or a nice, it can be used to define a nice sense of the size or the growth of the operator by noticing that basically the farther this particle on the chain, the farther this particle is in my picture from the left, the more complex or more complicated state in your Hilbert space or your Krylov basis needs to be employed in order to represent that state at time t. Okay, so basically what these people proposed is that one can associate the size of the operator or the complexity of the operator by the expectation value of n, or the position expectation value of the position of this particle on this one-dimensional chain. And they propose this working definition of complexity as the average position like this. So we have this probability distribution and we just sum over n, or with this coefficients n squared. Okay. And when I'll be talking about this spread or Krylov complexity, this will be exactly my definition in the most of my talk. So so basically, as this this expectation value of n in this probability distribution Pn in the Krylov basis. Sometimes I'll be denoting this C, this curly C of psi for the state, or for the operators as the K of O, for that, just to distinguish these two notations. But hopefully this should be clear that this is the same definition once you expand the state or the operator in this Krylov basis. And one can also think about this expectation. Yes?
Yeah. No, you should complete, but just to ask, I mean, the reason for weighting the phi n term with n is that somehow the thinking is that that you start originally with a simpler operator, is it? And then as the Hamiltonian acts on it more and more, it sort of becomes bigger or more complicated.
Exactly. I see. Exactly.
And this would sort of make sense if, in a sense, the operator you start with is tied to how the Hamiltonian arises. You know, what I'm saying is, for example, if you take the SYK model, we made out of fermions, say 4 of them or something, then it makes sense to think of a single fermion as somehow being a simple operator and how it grows, right? But if you choose a random operator and you know, which might be just squared to 1 or whatever, anyway, then it becomes a very then the definition becomes very dependent on how you started, right?
Of course, it's crucial how you start. So by this definition, you measure the distance in this kind of space to the operator that you started with. So if you start complicated, of course, you go like how beyond. The point is that you will not, well, in most of the cases, you like in integrable, yes, but in most of the interesting cases, you will not go from complicated to simple. Like you will go from complicated to more complicated, and that's what this kind of measures. But of course, there are examples that you can go from the most complicated to the simplest one, and we also have such a dynamic, say, in some integrable model. But the point is, like, it defines a nice notion, like, by in this process of evolving from some initial state.
So I along the same lines, I was thinking that if we had a local spin chain and we started with a local operator, then this n would tell us how non-local the operators become. So in that sense, starting with the local, in that context, starting with the local operator would be a reasonable thing.
Yes. Okay. Yes. So in spin chains, in fact, that's how this has been done in the past, mostly like just taking some spin chain and some simple, maybe some Pauli on some side, and then commuting it with your non-trivial Hamiltonian and seeing how this psi, say 10, spreads on this chain and so on. And then, you know, at each step you are like finding a new state in this, Krylov subspace. And okay, I'll be also mentioning that sometimes in this case, it's useful to think about this definition as an expectation value of some complexity operator that we can formally define as basically the sum over all the Krylov bases with these coefficients n. Okay, so this is this Krylov basic operator k psi, and then this complexity is just an expectation value of this in your state psi of t. And of course, I'm deliberately not writing what is the range of this sum. So again, this sum might be infinite, it might be finite, depending how many, you know, how non-trivial your state is and how non-trivial evolution is, and how many vector Hilbert, like non-trivial orthonormal vectors in this Krylov space you will. Okay.
Hello.
Yes.
Is this complexity always well defined? Because the sum can range to infinity, right?
Yes. So maybe what you are asking also is like there is some interesting examples, like questions about the convergence, and then indeed in most of the examples that we studied, this is well defined and convergent. But actually, there are usually some interesting examples where something non-trivial happens with this series. Let's say, what is the convergence radius of this or whatever, when does this series converge? And I don't think this, to my knowledge, this is not so well understood, like what is the breakdown of convergence reflecting in the system.
Okay.
So yeah, unfortunately I don't have a sharp answer what happens when this does not converge.
Okay, thank you.
Yeah, it's a very good question.
I have a question. Like, this is in regard to something that was asked earlier. Is the Krylov basis the same as is the dimensionality of the Krylov basis the same as the dimensionality of the Hilbert space under all circumstances?
No, generally no.
Because when you evolve a generic state psi naught by applying the evolution operator e to the IHT, is generally it will generally span the entire Hilbert space in the sense that it will go into a linear superposition of all the possible basis states of Hilbert space, right? In general.
Generically, yes, maybe.
Yeah. So in that case, when you say that the Krylov basis is not of the same dimensionality of the Hilbert space, then I'm
not saying like it can be, but it's not like, you know, as I was saying, that this definition is very general. I said like this H can be your physical Hamiltonian, but it can be any operator that you are like starting with and starting to evolve your state with. So I was trying to be deliberately very general in this sense that we have some explicit examples even with your original Hamiltonian. For example, you can take some harmonic oscillator and then you evolve your some operator X position, okay? And you might actually do this procedure by doing the commutators and so on, and you will see that this procedure will stop at 2 steps, right? Like at 2 steps, you will generate something trivial that you cannot orthonormalize anymore. So,
yeah, that is true. But I'm talking in terms of states.
I know, but like, so in that sense, I will associate the state with that evolution of x of t, and you know, even though the Hilbert space will be, say, infinite dimensional, you can still have Krylov basis will heavily depend on this initial operator or the initial state that you evolve with, and it will terminate at some order. So in general cases, you can, you know, the difference between the Hilbert space and the dimension of the Krylov, obviously from this definition, it is different. But they can be, like in most complicated cases, they can be actually the same. In most complicated dynamics and some generic state.
In general, for a Hamiltonian, they have to be the same. But as you say, for other operators, it might be different. That I guess.
Yes. Okay.
Hi, Pawel.
Yes.
Can I ask a very quick question?
Yes.
So it's very naive. So to understand this, this n in front of this sum, so it could be that for one of the lower values of n, the phi n is, let's say, much more larger. It has a high value, but that could still be dominated by some very large n, although for that particular n, phi n square may not be that large. So this can happen, right? In the sum.
I think I don't know like how. I think it's maybe related to this question of convergence and how generally like whether this is how these phi n's are distributed and so on. I think by this Schrödinger equation, and then of course it is also your questions are related to what are the possible ANs and BNs in any kind of dynamics and so on in this Schrödinger equation. In the examples that are kind of studied in the literature and that we also studied, it looks like this this of course this probability distribution depends on T. So like it usually looks like of course originally the state is picked at this initial point in this origin of this one-dimensional chain, but then as the evolution goes, the state spreads more to the right in some particular way. So it's not, and of course the sum of the probabilities has to go to 1. So you're like this, maybe these two, they're kind of sufficient to not to give you some crazy distributions, but I think in principle maybe I'm sorry, they are necessary maybe to give you some not crazy distribution, but maybe I don't know if this is sufficient condition. Maybe there are some complicated cases that I surely don't know that give you this behavior, because again, as I said, like this is very, very general. I mean, these definitions are simple.
I mean, for infinite sum, I guess I was a bit worried that, I mean, their n could be as large as possible. And
okay, so that I will show you some examples with infinite.
Okay.
So this will actually be quite nice.
Okay, thank you.
Okay, so good. So let me just make some comments that maybe clarify or they touch upon some of these things that you already actually mentioned. So basically, what we were trying to define with this in this paper by Vijay is like some maybe more intuition or more intuitive notion behind this Krylov complexity, and basically, as some of you already mentioned this, so when we study this psi of t as e to the minus iht of some initial state, it might be natural to define some notion of complexity by how the state, this initial state psi 0 spreads in the Hilbert space by this unitary evolution. Okay, and how would you go about defining such a notion? Well, basically, what we did was we defined a basis B in some ordered way, in a sense that you define these basis vectors labeled by n with n equals 0, 1, 2, and so on, such that this B0, the initial vector, is always chosen to be the same as this psi 0 vector. Okay, so in particular, this Bn might be a Krylov basis, as I was defining before, but here we want to be more general. And then we propose that you can actually define a cost function or a family cost functions by basically projecting your state psi of t on this basis, okay? And then doing the sum over with the coefficient Cn on each of these basis vectors in this following ways. So basically, we define a cost function C of beta of t by an absolute value overlap of the state psi of t on the basis vector n, and then we sum it with the Cn like this. So this, of course, this is, in other words, it's basically some probability distribution weighted by this coefficient Cn. And for the Krylov complexity, this Cn's are chosen to be n, but in general, we can take them to be any positive, for these arguments at least, we can take them to any positive coefficients of the integer n. And then what we managed to show is that actually, if we now minimize this notion of complexity, okay, over all the choices of the bases, So basically, we minimize over choices of B in the subset of the basis vectors for a finite amount of time. So of course, minimizing for any t would be kind of trivial, but we want to minimize it, like, let's say, for some sufficient amount of time to find this basis that gives the minimal value of this cost function such that it supports the state, the growth of the state for finite time. Then actually this minimum is given by the Krylov basis. And
sorry, I didn't understand. So what was the minimization procedure? Sorry, just
okay. So we basically define this cost function, okay?
Yes.
And we define this cost function for any basis. You choose your favorite basis, Bn, such that it has this initial state to be B0. You project your state on that basis, and you compute this cost function, okay? So now we tell you, like, to define this complexity, we will tell you that you choose this cost function with this coefficient Cn and then minimize over the choice of the basis for some finite amount of time. So for example, compute it for your favorite basis 1, compute it for your favorite basis 2, and choose the minimal basis that gives you the minimal value of this cost function Cb of t. Okay.
Right, but where does the time come in? Just you have some set of basis functions.
Yeah.
Among them, you choose the one which does best.
That's right. That's right. But you need to choose that. You need to choose the basis that will support the evolution of your state for some finite amount of time. Hopefully, like for all this time, because like you could always It was very intuitive to understand it when you do a discrete time evolution. So let's say you start with some initial state at time t equals at time 1, and after one step of time you apply one, you apply one Hamilton, and so on and so on. So basically, in this discrete time, it's clear that basically if you choose this coefficient Cn to be positive, any state can be always written as a state basically obtained by Gram-Schmidt orthogonalization, or the new state in the Krylov basis plus some other plus some state that requires more elements in the Krylov basis. But as long as the Cn's are positive, this value of the cost function will be bigger than the one only from the Gram-Schmidt orthogonalization.
Okay. I think I'm getting the sense. Okay, thank you. And sorry, Pawel, to interrupt so much. But one other thing is, when you optimize or extremize over the set of bases, what are you doing with Cn's? The Cn's are kept fixed regardless of bases.
Cn's are fixed. Thank you. Cn's are fixed. So you define this cost function for a particular choice of Cn's. They can be, in particular for the Krylov, they are really Cn's to be n, but you could choose them as long as they are positive. This argument will go through.
Positive and increasing with n, or even that's not necessary.
Positive in n and increasing with n.
Okay, thank you.
Yes. Okay, so that's just a comment, and in the paper we tried to do it also for continuous time, and actually, you need to tell me like how to do some ordering of all the derivatives at t equal to 0 and so on. So it's a little bit technical, but you can actually show that also for continuous time, this Krylov basis gives you the minimum here. Okay,
and this minimization is true for all time, that they will give the Krylov basis.
For continuous, we only managed to prove it for finite amount of time, but it's like for that you need like some order. We did like some induction proof. So we compute some up to nth derivative at t equal to 0, and then we could show that this also goes for n plus 1 and so on. But formally, in that proof, we proving it for finite time, very large time, but it's finite. It's not infinite. So maybe we believe that there should be a better proof that goes for infinite times, but we were not able to find that proof for continuous time.
Okay, and this is the Krylov basis is also minimal for any Cn's.
Yes, for any positive increasing Cn's, yes.
Okay. Yeah.
Thanks.
Wait, I have a question. I mean, the Krylov basis, for different Cn's, the CT would be different, right?
Exactly. So you fix your Cn's.
Yeah.
You fix them as function of n.
Once you change the Cn once you choose a Cn different from n, you will get a different CT. right?
Of course. So the point is like this cost function, you can choose two cost functions, one defined with cns being n and another cost function with cns being n square. Okay.
Yeah.
And the point is that you again do this projection on your basis and you minimize those functions, let's say with cns being n and cn being n square. And it doesn't matter which cns you chose, like both minimas, they will be different, of course, for n and n square, but both they will be minimal for this Krylov basis. That was the state.
Okay.
Is that clear?
Okay. Yeah.
Okay, maybe the main point is that once we expand the state or the operator in the Krylov basis, we are getting this probability distributions of phi n squares or pn's. And basically, this is all about this state. Okay. So again, I've been stressing it from the very beginning so many times already, but this is really important. You start with some initial state psi 0 or some initial operator all that you mapped into some initial state psi 0, and then you do this evolution with the Hamiltonian or the Liouvillean that generates you some dynamics. But basically, once you expand this in this Krylov basis, there's nothing more. This is all the information about your state, about the evolution of this initial state or spread of this state for any times t. Okay, so basically now the question is, once you have that probability distribution that tells you how this evolution goes, you can characterize it in many ways. So here I just told you that, choosing n is a nice intuitive definition of distance or complexity, but you can actually compute like what's the information content. Like this is usually called K entropy, which will be like the Shannon entropy of this probability distribution. You can choose higher moments, like you might complain, why did you choose n and not n squared? So there's a way of doing this. There's a way of doing this in some systematic way. For example, you choose average position, but you can also ask the question, what's the variance around that mean value? So this is usually referred to K variance and K cap. We can also define something called K capacity by some means, or we can also compute. There are some nice notions by taking, for example, exponent of this K entropy and so on. And generically, again, for some interesting evolutions, the average position or even this K entropy will not be, again, enough to fully characterize this probability distribution. So now from this probability, we extract some information. But the interesting thing is that the whole evolution is captured by this probability Pn. Okay. And so up to now, I've been talking about some very general things and, very kind of broad definitions, but I think it's very useful to go to some explicit examples where actually you can see how it works and what kind of data comes into this definition. So do I still have time to, actually, how much time do I have?
Yeah, so you can continue.
Okay.
Yeah, as long as you know. Yeah.
Okay. So I'm going to go into examples, but are there any questions about what I have said so far? Okay. So maybe now I motivated my talk by this canonical examples where we need complexity. So let me now convince you that actually we can, using this Krylov complexity or spread complexity, we can actually apply this definition into these examples that we really want. Okay, so first example will be this time evolution of the thermofield double state. So consider this TFD state, which is this purification of the thermal state, sum over the energies of two CFTs, for example, but you can do it, of course, for general TFD state with the e to the minus beta over 2En, where z of beta is your thermal partition function. So now when we do the time evolution, we consider, again, this thermal field double with e to the minus IHT, where this H can be left plus right Hamiltonian or either left or right Hamiltonian. And our goal is now to expand this state in the Krylov basis and compute this complexity associated with that probability distribution of the state in this basis. And I told you that the crucial thing actually in the story are the moments of this return amplitude, from which we can extract Lanczos coefficients and then find this coefficients phi n's by solving the equation and compute actually what is this spread or K complex. So in this case, when we do when we compute the return amplitude will be an overlap between the thermofield double at t equal to 0 and also this thermofield double at time t. And actually, this is from the definition of the thermofield double, that becomes just a ratio of two partition functions, these thermal ones. The thermal partition function with beta shifted to minus it. This basically comes from the definition, normalized by the partition function at z equals to beta. So maybe you are familiar with that this is precisely the amplitude that appears in the so-called spectral form factor, okay? And basically, in order to compute this Krylov complexity, now we should study this non-universal amplitude in the spectral form factor and extract from it Lanczos coefficients and these probabilities and so on. But let me stress again that this is completely non-universal. So as long as you have some z of beta, you can apply this definition and compute whether this spread of TFD in that model is simple or trivial. But in principle, knowing z of beta, it can be done. Okay, even if we know it, for example, in some limits, like limit of large CCFTs and so on, that this is already some interesting part of the evolution that can be extracted from this partition fund.
So the spectral form factor is ZZ star. I mean,
yes. So this is an amplitude. So spectral form factor will take you the absolute value square of that. Okay, so let me just show you one example where this can be done in a very efficient way. So we know that the spectral form factor, some kind of interesting and universal feature that should be associated with some late time also dynamics of black hole can be seen in the spectral form factor of some random matrix theory. So let's just apply these definitions that I told you to this context of random matrices. So in other words, let's consider some Hamiltonian to be some n by n Hermitian matrix. So one of the ensembles. So this can be, for example, GUE or orthogonal or symplectic ensemble. So I just chose some simple matrix 3 by 3 with some random entries, but we can do it for very large n in a very efficient way. And basically, what we can do, of course, is we can just numerically diagonalize it and compute the spectral form factor, its moments, Lanczos coefficients, etc. But the main point is that, as I was showing you from this algorithm, you want to put this matrix into this tri-diagonal form, this Hessenberg form, and read off what are these ANs and BNs, okay? And actually, there exist very efficient algorithms and libraries in Python or even in Mathematica to put a matrix of a very large size numerically into this Hessenberg form. So actually, we can put this random h to that form and read off immediately the Lanczos coefficients by that procedure.
I have a question here. So this matrix, this A0, B1, B1, this is a representation of the Hamiltonian?
Yes, in the Krylov basis.
In the Krylov basis, yeah. But this is in reference to what Sandeep was asking earlier. I mean, this doesn't look manifestly Hermitian, because if the B1s and the B2s are complex, then this
Yes. So by construction, they are this is going to be a Hermitian matrix by construction of this Lanczos algorithm and unitary.
But if the B1s are complex, then how
they are real. They are real. So like even if we take this, as long as H is Hermitian, then this ANs and BNs, they will be real.
Okay.
Yes. And okay, so there's one trick. Basically,
one question. So when you say that any Hermitian matrix can be put into this trigonal form, you have to supplement this question with a size 0, right?
Excuse me.
You have to supplement one vector also.
Yes. Very good. Yes. So the point is that exactly. So that's precise the point. In these libraries, they have this form, and then they are usually this form when you compute it, when you extract it numerically, it's usually defined for this initial vector to be of the form 1, 0, 0, 0, 0, okay? And so, of course, the point is that for us, for a particular Hamiltonian, once we diagonalize, we can write down explicitly what's going to be our thermophile double state. And then we should, there's an intermediate step, we should first rotate this thermophile double state into this form. And then basically the rotated Hamiltonian, we find exactly this particular ANs and BNs such that, such that it corresponds to our thermophile double state. That's an important point. Thank you very much. But then once we have this form, we can simply, again, numerically exponentiate, so take e to the IHT, and then apply it into this initial vector, and that will immediately generate for us all the finite numbers of phi n of t for this random matrix. So basically, this is just some numerical algorithm to get all the way to the coefficients, to the probabilities that we want, okay? And let me just show you how, what kind of data can we get from that. So here on the plot, I'm doing the matrix H to be drawn from the GUE, and then we studied N, the size of this matrix, up to 4096. So as you can see, like there's a pretty good numerical algorithm to extract this form of the matrix for very large matrices, and this works pretty well. But I have to say that, the work was done by this really great student of VJ, that he is also an expert on Python and so on. So maybe, if you will try to do it at first on your laptop, maybe you will not be able to go to that number of N's. But anyway, you can efficiently extract what these ANs are and what the BNs are. And you can see that we plotted them here as functions of N over the size capital N. And maybe it's good to plot them actually in more detail here. So you see that initially both of them grow from some initial value. Actually, these ANs, they can be negative at some initial values. And then, of course, BNs, they are positive, and they are chosen such that this B0 was always 0, okay? So, but you see that they evolve with N in a particular way, so they grow, but then they saturate ANs for some particular value of N over N, goes to value 0, but then BN, they go up to 1, and they saturate at this value at more or less the same time. This feature also, it's interesting to probe, maybe I will show you some analytic example. It's interesting to probe this AN minus 2 BNs, and you see that there's some difference between that, but for late times, this combination AN minus 2BN, that becomes like some constant. And that will be important in my analytic example. You will see that this particular value when AN minus 2BN leads to some particular behavior of this coefficient. So remember that. Okay, so
I have a question here.
Yes.
Is there any particular reason why the ANs and the BNs don't develop imaginary coefficients or imaginary?
I think in these cases it's just by unitarity. It's by the dynamics and this Lanczos algorithm, they are constructed in such a way that they will not be imaginary. We studied some examples, and people also in the literature, where you do some open quantum system or some non-unitary evolution, and there you can see that BNs become imaginary generically if you just naively apply this Lanczos algorithm.
BNs become imaginary?
Yeah, they can get imaginary parts if you study some non-unitary dynamics.
Oh.
And apply Lanczos algorithm. But maybe the lesson from that is probably that you should be using some other algorithms and not the Lanczos one for this unit that is done for this. Okay, so let me just show you some universal, like how does this proceeds, this evolution for this thermophile double. Maybe at initial times it's actually quite universal. So you can see that initially it grows quadratically at early times, as it should. So this is, I'm plotting here the complexity, the C of t. This is this spread or Krylov complexity normalized by beta 2 inverse, and then it's plotted as a function of time to some particular power. That was not just done to make this plot clear. And then we have some initial quadratic growth of this complexity. But actually, we have plotted also it for many examples for different choices of beta. So beta is this inverse temperature of your thermophile double state. And then we plotted as a function T over N. And actually, when we plot this complexity, well, again, normalized by this size n, we actually observe four universal regimes or four regimes in the evolution of this complexity. Namely, first we have some ramp where this complexity grows. Well, of course, after this initial quadratic growth at very early times, we observe that this complexity grows in this ramp form. Then it reaches the peak. Then it has some slope part that goes a little bit down, and then it saturates at something that we call the plateau. Okay, and we have studied this for all these sizes, but for many choices of random matrices. So, for example, we took also orthogonal, symplectic, and also we looked at SYK explicitly, and we saw this universal behavior of, I mean, these universal phases of Krylov complexity for this random matrix.
Sorry, Pawel, one question. Maybe this is something that you mentioned I missed. What is complex TFT? What is TFT evolved with GUE Hamiltonian? I mean, what is the time dependence?
Yeah. So, okay. So basically, you can take any system. Sorry, I don't know. You can take any system, okay, yeah, with some Hamiltonian being n by n matrix, okay, Hermitian. Okay. You diagonalize this matrix to find ENs.
Okay.
You put it into this thermophile double state.
Okay.
And then you just do this time evolution. Okay.
And then you do this for various Hamiltonians.
Exactly. So you can study it for various Hamiltonians depending on the size and depending on the temperature.
I see.
And
so when you say matrix, random matrix theory, you pick one particular instance when you're showing these results. You're picking one particular instance of it, or you're averaging in any way?
I'm not averaging. I'm just picking one particular instance. Yes.
Yes. Thank you.
And for that instance, I'm recomputing everything, and I'm making one of these curves is the plot for particular beta and one random matrix of this size. Thank you for this.
Now, if we average, also, does this have any features, or maybe you will say?
Yeah, we have. Well, we have not studied this averaging too carefully, so we don't know.
Okay.
This is done for, well, there is some kind of averaging in a plot here, in a sense that we have like many values here for this particular choice of beta for all this, and they all behave in a similar way. So, but there can be some, by choosing some appropriate averaging, there might be also some physics related to that. So I don't know for sure.
Okay.
Usually for the spectral form factor, the wiggles disappear when you take that's all that happens.
Yeah. Okay. So let me just show you some, let me just give you some understanding of it from this probability distribution. And actually, this is kind of nice. So first, notice that on this left bottom corner, sorry, I think there's some maybe somebody had to leave. Okay. So at this left bottom corner, what you can see is that indeed, at time t equal to 0, this probability is picked at, at this initial state 0. And then as time progresses, this evolution in this Krylov space spreads like some kind of, like some kind of tsunami peak to the right that starts from the left to the right. This is in this setup. Sorry, is it clear what I'm plotting here? Is this probability distribution in the Krylov basis, this phi n defined by these coefficients, like here. This is, I'm plotting exactly this probability distribution as a function of t. So I just realized that there was no caption on this plot.
X-axis is n, is it?
So x-axis is n, yes.
Okay.
So I'm going exactly, and I'm plotting it for different instances of time. And you see that indeed, initially we are picked at n equal to 0, and then this tsunami propagates to the right. And actually this peak, so this is this ramp part. This peak part corresponds to the time where we reach the most complicated state in the Krylov basis. Of course, because we are now having finite dimensional matrix, there will be we're going to reach the most complicated vector after some steps. And this peak, after this peak, we reach the most complicated one. Then actually this probability distribution somehow bounces back and starts kind of equilibrating. That's exactly the slope when we reach the most complicated one, and we are trying to go back, so to make sure that now every state becomes equally probable. And this is exactly the plateau. The plateau is reached where this probability is like randomly distributed on all the basis vectors in the Krylov space. Okay, so that's kind of a nice feature of this evolution in the Krylov basis. And of course, there's some also dependence on the temperature. So beta equals to 0 is this most dark one, then the one below is for beta equals to 1, and all the way up to beta equals to 10. One interesting feature is that we also studied is basically what is exactly the origin of this, peak and then the plateau. And we realized that this can be made very sharp in a sense that this peak and slope, the peak and slope, they are related to the non-trivial correlations between eigenvalues of these random matrices. In a sense that, for example, you see that there's this dark blue picture, there's this dark blue curve on the top, and it has the same plateau as this kind of lighter blue curve that goes there to the plateau, but without the peak and the slope. So what's the difference between those two? So this lighter blue curve is basically the curve where we chose the eigenvalues of this n by n random matrix, but not by just diagonalizing it, but we chose it at random from the semicircle distribution. So we know that this procedure precisely gets rid of this non-trivial correlations between eigenvalues, and actually in that procedure you see that you wash away the peak and slope. We have done the similar example for the spectral form factor. So you see at the bottom, if you plot the log of the spectral form factor as a log of t, you see that the spectral form factor has also these 4 regions like slope, deep, ramp, and plateau. But if you just draw their eigenvalues at random from the semicircle, you actually get rid. This is this lighter curve here. You get rid of the deep and the ramp, and you go basically from the slope all the way to plateau. So actually, this Krylov complexity or the spread complexity is exactly sensitive to this phenomenon as the spectral form factor on the correlations between energy distribution.
Sorry, I have a naive question.
Yes.
When the Hamiltonian is when you say that when you say that the Hamiltonian is random matrix Hamiltonian of dimension n,
yes.
Does that mean that the Hilbert space is also of dimensionality n?
Yes.
But then you, in general, when you expand in terms of the Krylov basis, it goes past n, right? In general,
it goes past n.
What is the dimensionality of the Krylov basis when the random matrix Hamiltonian is say 3, for instance?
Yeah, so at max, for this, it's like as the dimensionality of the Hilbert space.
So the Krylov basis is also of dimensionality 3, you're saying?
Yes.
When the random matrix Hamiltonian is 3 dimensionality?
Yes. You cannot go beyond the dimension of the Hilbert space.
Okay. No, but what I was concerned about was that suppose you take h to the, you consider taking powers of h acting on the state psi naught, then in general you can generate all sorts of states, right? You can generate states up to for n up to infinity, right? So those would be dependent on the first 3, you're saying?
Okay, but like they will be yes. You can only you expand it in a basis that it's as most that has as many elements as the dimension of the Hilbert space.
So you're saying that the expansion will truncate at h to the 3 on psi naught.
No, the expansion might not truncate, but you will not need like more complicated vectors to.
Pawel, if we, how does the time taken for this peak to hit the edge, how does that scale with the n? Is that linear with n?
Yes. So in this time where we reach this is of order the entropy, exponential of the entropy, so exponent of the n.
So is that what you call capital N here?
Yes.
So size of the Hilbert space. Okay, excellent. And is that roughly speaking the same as the time taken to reach the dip in your spectral form factor?
It's a very good question. Yeah, we don't like, somehow it was very difficult to extract whether to make this sharp, whether the time where we reach the peak is exactly the time where we reach the dip in this one, because the scales were kind of like log and log of t. So we have spent a lot of time arguing whether this is exactly the same time or not, but I think this is not obvious. What is obvious that we have these 4 regions the same way as in the spectral form factor, but we are not 100% sure if they correspond to exactly the same time for this random matrix case that we were able to study.
Okay, great.
Like, numerically, we could see that, okay, it roughly looks the same, but I think that it was a strong statement to make sure whether this is precisely that time.
Great, great. And then the time scale for plateauing in the top graph is also roughly n.
Yes, yes.
Okay. Thank you.
Yeah. Okay. So okay. I think I have been already going for some time, so maybe.
Yeah. So how much time do you think you will need, Pawel?
I can basically just show one more example for the operator graph quickly, and then I can.
Okay. Yeah, that would be great.
So yeah, basically I was trying to use some. It's also I showed you that there are some examples where you can use numerics, and this is nice, but also it's very kind of sometimes useful to use analytics, and there are some basically cases that are also determined by the symmetry. So let me show you one example where that you can actually solve all the algorithm and all the evolution analytically, and actually this also corresponds to infinite dimensional Hilbert space, and it's probably good to have some feeling what can this coefficient be like. So let's consider this abstract, of course, abstractly just this SL2R, where we have L0, L1, and L minus 1, and what we can consider is basically a natural basis in this for this Lie algebra, in which, of course, L0 is the diagonal with coefficient h plus n, and L minus 1, it's the rising operator, and L1 is the lowering operator. So just for fun, let's consider some Hamiltonian evolution with the Hamiltonian that is built by these generators of the SL2R algebra with particular coefficient gamma L0 and alpha coefficient of L1 and L minus 1. Then if you consider that and you take this for the Krylov basis vectors to be this basis of the algebra, where you take some highest weight state h and act L minus 1 to the power n, you can show that this for this Hamiltonian, this basis is actually the Krylov basis. So it's the basis in which this Hamiltonian is tridiagonal, obviously with a coefficients an being proportional to this n plus h, and then with bn's being with some coefficient alpha being proportional to this the coefficient of the lowering operator, and then basically this this is exactly the representation of this kind of algebra like Hamiltonian or symmetry generating Hamiltonian in the natural basis. Okay. And basically, if you consider a state psi of t that has this e to the minus iht with that Hamiltonian on some highest weight state, then you can use Becker-Campbell-Hausdorff to find explicitly what these phi n's are in this Lie algebra basis. And you can check that explicitly that they solve the Schrödinger equation with precisely these an's and bn's of the basis. So also with that you can compute, for example, this Krylov complexity. And in this case, of course, first of all, this probability, this sum goes from n equals to 0 to infinity. So we have like sum over, so we have infinite number of Krylov basis vectors, infinite number of probability amplitudes, and they all, of course, converge and sum up to 1. And in that case, you can actually compute explicitly this Krylov complexity or spread complexity, so computing sum over Pn with n, with, and this is proportional to this highest weight state h, and also depends on these coefficients alpha and beta that you have in the Hamiltonian. Here, these are alpha and gamma of the Hamiltonian in this way. So you can see that as long as this combination 1 minus gamma square over 4 alpha square is real, then this goes as basically for late times, this goes exponentially in time. But there's this particular combination where actually this gamma is equal to 2 alpha. And this corresponds precisely to this notion I told you before, where when ANs are proportional to 2 times BNs, and in this combination, the growth of the complexity slows down. It basically becomes quadratic in t instead of exponential at late time. And even there, you can show that if you naively continue it for the values such that this becomes imaginary, then this complexity is not anymore growing, but is actually oscillating like sine function and so on. Moreover, you can check that this complexity that we have just computed, it actually is proportional to the value. It actually is, it corresponds to the fluctuation of the expectation value of L0 operator in this algebra. So if you compute L0 for the state at psi t and subtract L0 at time t equal to 0, this is going to be exactly this value. Okay, so my my point was that there are some analytic examples for infinite dimensional bases that you can solve and get some feeling what these ANs and BNs are in some simple examples. But second thing is that actually I wanted to show you that this example of SL2R is actually not just a mathematical trick, but it actually corresponds to a particular growth of operators in the SYK model. So what this was actually done in this paper by the Berkeley group, where they consider the growth of the operator with appropriate choice of the inner product, such that this return amplitude or the 2-point function was given by some cosine hyperbolic of pi t over beta to some power eta, where eta roughly in like some QSYK model at large Q was scaling like 2 over Q. Okay. And then they managed to show this for this return amplitude, that the growth of the operator corresponds to this BNs growing linearly with n at large n, and also with this amplitude given by this particular function. And so what they argue, and of course then they observe that for late times, this Krylov complexity, or the operator size defined by this Krylov complexity at late times, grows exponentially with time, with some coefficient being a lambda, like that they call Lyapunov exponent, to being the same coefficient as 2 pi over beta, or this maximal Lyapunov that you see sometimes in ODOC correlators. And basically that led them to this hypothesis that maybe, you know, when we study some growth of the operators in chaotic systems versus integrable systems, the maximal possible growth of these coefficients Bn is linear at late times, and then from this linear growth, you can extract the coefficients that should be related to the Lyapunov coefficients of out-of-time order correlators that you also study for the growth of the operators. That was their hypothesis. And this was the picture of different BNs for integrable, chaotic, like SYK models and so on. So basically, you can show that this SYK example, this can be exactly phrased in the language of this SL2R coherent states, or this SL2R algebra that I showed you in the slide before. Namely, if you just consider this Liouvillean for the operators to be just given by alpha times L1 plus AL minus 1. So in my previous Hamiltonian, that was just gamma set to 0. Then this state that represents the growth of the operator, it's given by some displacement operator. That is basically this object acting on this highest weight state of that algebra. And you can show that the growth of the operator actually corresponds to a certain trajectory in this phase space of coherent states of SL2R algebra. And yes, so basically for this particular choices of gamma, we can indeed see that this explicit solution that we can find is just governed by the SL2 algebra that is, of course, somehow also responsible for fixing the symmetry of these 2-point functions in, say, this chiral CFT that gives you this particular value. Okay, and going maybe beyond that, we can actually show that this growth in the in the phase space, this trajectory in the phase space can be shown in a very nice geometric way. Namely, we can compute the Fubini study metric on this in this Hilbert space spanned by coherent states, and that Fubini study becomes basically a metric of a hyperbolic disk, and the growth of the operator corresponds to some trajectory from the origin up to some position rho equals to 2 alpha t on this disk. And if you are familiar with the growth, like these geometric notions of complexity, basically you can check that in this information geometry, the Krylov complexity that we computed, this particular value here for the operators here, corresponds actually to the volume in this phase space. So if you compute the volume in this phase space up to some radius 2 times alpha t, it goes like pi times this Krylov complexity. Moreover, maybe this was a little bit fast, but you can actually show that this complexity K0, I showed you that this is basically a fluctuation of this L0 operator in this geometry algebra. This Krylov complexity operator becomes just a generator L0, or actually the killing vector corresponding to L0 in this hyperbolic geometry. So there is the nice way of geometrizing this Krylov complexity growth or Krylov complexity operator and that geometry of ADS or Euclidean ADS2. So basically the cartoon is that we start with some phase space that is given by hyperbolic geometry or Euclidean ADS2, and then the growth of the operator corresponds to this red trajectory starting from the origin up to some radius alpha times t, and then this Krylov complexity is actually not the geodesic length from the origin up to this point, but actually this volume that is captured by this growing circle. So this is kind of geometric interpretation, at least in this symmetry setups for SYK or for some simple operators where you can use the algebra to geometrize this complex. Okay, so I'm really sorry for taking so much time, but I wanted to convince you that there is actually a new universal definition of spread or Krylov complexity that we can apply both to states and operators as we really wanted at the origin of all this program. And this definition is algorithmic. So basically via this expansion of the state in the Krylov basis, we are getting some probability distribution. And from there, we can characterize this evolution by either computing average expectation value of the position, which is this Krylov complexity, but we can also compute, say, some K entropy and other quantities. And finally, this definition gives us a tool to compute the complexity of the evolution of the thermofield doubles, let's say in random matrices, and that leads to this universal behavior or 4 distinct parts, which is ramp, peak, slope, and plateau. I didn't have much time, but I tried to also argue that there is this symmetry angle on this Lanczos algorithm. Actually, people before just studied numerically for some many-body systems, but we can now try to look at it from the perspective of symmetry or some universal behavior governed by some more complicated Lie algebras. And this works very well for some operators in SYK or also in 2D CFTs that I did not have much time to talk about. Finally, the questions that you should have after this talk is like, why on earth Krylov basis? Of course, it's a basis in some swap space, but generally we know that physics should be kind of invariant under we change like from one basis to another. Still seems like this Krylov basis is kind of special, and it really measures how complicated operations you applied, how many Hamiltonian evolutions you have been doing. So it's kind of a special basis in this subspace, but we still don't understand why should it be special, especially for holography. There has been some, so in particular, can we understand from the bulk? We understand roughly bulk for the thermofield double and its evolution, but can we understand the bulk interpretation for this higher Krylov basis vectors? I think that would be interesting. Some steps towards this, they have been done by Henry Lin, where he tried to make some connection in some double-scaled SYK and chord diagrams and this Krylov complexity, but it's still very fresh. And finally, we'd like to know whether there are some universal laws of spread complexity. Is it actually used, this way of thinking about complexity? Is it useful for quantum information or quantum computation? We still don't know that. Of course, how does it behave generally for holographic CFTs, large and models? There's still a lot to do. And finally, making this precise connection with holography or near horizon geometries that I motivated at the beginning is still a part of the things that we are doing. So thank you so much for your attention, and sorry for going so much over time, but your questions were really fantastic. So that's all I have to say.
Thank you very much, Pawel, for a wonderful talk. Let's all launch. So we had many questions during the talk, but if there are a couple more urgent ones, then maybe we can ask Pawel.
Sorry,
can I ask one?
Sorry,
so I just wanted to ask. Thanks for a very nice talk. I just wanted to ask. You were saying one good thing about using the Krylov base is this fact that the spread of the wave function is minimized over all choice of bases, right? But at some point you also picked an inner product. Can you show some? Is there some similar result with choices of inner products also?
So yeah. So in here, when in here, when I talked about this minimization, I choose already this natural inner product between the state and the stated, basis vector and the stated t. Mm-hmm. So this was for the definition. This what I talked about here it was for the definition of the spread of states.
Right.
Okay. So when I talked about the inner product, that was in the story for the growth of operators. So I start with this abstract growth of the operator in the space of operators, and then I need to choose an inner product to have some meaningful map from the space of operators into a space of states. But after I chose this this inner product, then I'm going to end up with this problem number 1. So I'm going to have some initial state psi 0. Okay, and then I will do some evolution, blah, blah, blah. So again, this logic applies. So this was mostly for the evolution of states.
Right. So if you wanted to make this argument for the operators, right, not for the states, that some of the Krylov complexity is nice because it minimizes the spread of operators.
Yes.
Then to say that, you'd have to choose first an inner product to map that problem to sort of this one, right?
Well, let's see. I've been thinking about more like I would need to choose the inner product that would just give me a different form here. It would still just give me some psi of t times e to the iht times psi 0. Or maybe a better way to say it is like here. I could always choose, like, you tell me that, okay, your inner product is this one, and then you choose some evolution of such operator with such inner product. I claim that I can choose some state psi of t that will maybe not be like as simple as that, but I can choose the state that will have the same return amplitude or the same growth of that operator. Maybe different for different choices of the inner product, but it will still be some state of this type. And then I'm coming back to this step number 1, and then I'm again defining, this cost by the usual inner product between states in the Hilbert space. But maybe your different choice of the inner product will correspond to different psi's of t's for maybe for the same operator, but for 2 different inner products. At least that's how I would think about it for 2 different inner products. The point is, like, as long as you just choose some as long as you choose the same return amplitude, okay, for your, let's say, you can choose, like, it might happen that you choose like some operator 1 with some inner product and operator 2 with some other inner product, but as long as they have return amplitude or mappable to each other, then you're going to have the same moments, a simple relation between moments, the same Lanczos coefficients, and eventually, the Schrödinger equation is just sensitive to that. So that will just give you the same value of the spread complexity for the same return amplitudes. I hope that clarifies.
Yeah, sorry, very quick question. Well, maybe you've said this and I missed it, but you started your talk with talking about how this length of the wormhole grows with time in a geometrical setup. And then by the end, you sort of with your definition of the Krylov complexity, if I understood right, you could more or less compute the rate of growth with time of this complexity in a thermofield
Yes.
setting. Do these two numbers match? Firstly, is that a well-posed question? And secondly, what's the
It is. I think it is a well-posed question. The computation that we have done was in some random matrix example. Okay, so to really do the matching, we would need to do it in some some 2D CFT at least, where we can compute some growth of the volume in ADS, or well, maybe in ADS2 this could also be possible. But we have not done this. We have not up to now. We have not done this in a kind of explicitly holographic setup where we can have geometric computation and field theory computation. This was done in the random matrices, right?
Yeah, but I was thinking this, and please, it's probably very stupid, but I was thinking that, say we fix a particular energy,
yes,
in the bulk setting, then we have, because we know the entropy of our system, we have a particular effective Hilbert space of a certain dimension. And now the Hamiltonian is sort of, I was thinking, I should say more clearly, I was thinking that if we have a particular Hamiltonian whose spectrum we know in the bulk, because we know the effective free energy of the black hole. From that Hamiltonian and from your definition, we should be able to just predict how the complexity grows with time, and then compare with the bulk. Is that wrong?
Yeah, I think.
Yeah.
In principle, I agree with you.
Okay. But you're saying it's not
I have not done this exercise, let's say.
Yeah, okay, fine. Okay, thank you.
Can I ask one question?
Yes, sure.
Yeah, so thank you for your talk. So this is about, So if you take a Hamiltonian with some coupling constant, which is say the coefficient of some nonlinear term, and if you study in some simple model, I guess you can numerically study this. Does one know how the dimension of the Krylov subspace change as you tune your coupling constant? So you can go from the free or integrable case to where it becomes, you have strong nonlinearity. So is it in some simple model study, like how, is it probably reasonable to expect that it grows as you, like for more chaotic systems, you expect a larger dimension for the Krylov subspace, or is anything known?
I think it naively it should grow if you just break this integrability or go to more complicated setup. But and actually, I'm sure people have studied that, because this is kind of like one of those probably old questions that people have been asking already in the 60s. But I'm not aware of any simple example I could just tell you at on the top of my head. So I'm sorry. I also expect it should just grow, but how it grows, I don't know.
Okay, thanks for your talk.
I have a question.
If there are, okay.
So this various BNs, they are simply matrix elements of powers of H between psi naught and psi naught, right?
These are the mu-n's.
The BNs I'm talking about in the Hessenberg.
Yes. So they are defined. You see these BNs
how are they defined?
This matrix elements of H in the psi naught. These are the mu-n's.
Oh, mu-n's. So how are the BNs
these
defined?
are just the ordinary moments, okay? And then these moments, they are related in a non-trivial way to some polynomial way to this BN coefficients.
Yeah. So now, in general, these mu-n's would in general be complex, right?
Mu-n's, the way they are defined here, yes, they can be complex.
Because arbitrary power of H in general would be complex.
H, yes.
If H is complex. Now, why would you expect that when you extract the A0s, the ANs and the BNs from these various mu-n's,
Yes.
you expect that the ANs and the BNs will all be real?
Well, they are just like given by this polynomial quadratic like relations. Okay. Yeah, say from this algorithm, you see that. Well, so there is always this I here that comes, you know, with some powers to the mu-n, but you can see that from this algorithms, basically, all that will appear. It will be just some real numbers.
I mean, is that obvious from this expression that manifest?
Well, let's see. So the point is like, you see, of course, you construct it by this way, and then, but the point is like you have this Schrödinger equation that comes from the unitarity and also this unitary evolution. Okay, so once you define them this way, once you hit it with time, then basically this for this probability, you know, for just from the unitary, you can see that this coefficient should not be imaginary. This bn's and bn plus 1. If they were imaginary, then yeah, you will get some funny, like they would not. Yeah, this I think that would even, because even in that that whatever basis you choose, this e to the minus iht, this has to be. Yeah, this has to be a unitary operator, right? You're saying that there might be still bn's that are like imaginary, but such that this is
in general,
unitary.
the ANs and the BNs are defined in terms of the mu-n's. So the mu-n's are in general complex. So is there any reason why, I mean, why is it manifest that the ANs and the BNs will be real in spite of the mu-n's being complex?
Well, I don't know any like a clear example. I thought like at least in all the examples that I have studied, they're always real. There might be positive or negative, that's fine, but like they're always real numbers. And I think this comes from this is a consequence of this unitarity, but maybe I'm wrong, and definitely the ones I've seen, they were in some non-unitary evolution where bn's were becoming imaginary. That's why I'm making this statement. But I don't know. Maybe there is like there's some more general example where these bn's could be imaginary, even in the, I don't know, maybe some non-Hermitian evolution or something like that.
Okay. Can I just, sorry, one small question and then we'll let you go. If you compare this thing that you are comparing, the spread of the complexity with the spectral form factor, and we had the statement that the peak in the complexity occurs roughly at the same, maybe occurs roughly at the same time as the dip in the.
Yes.
But the spectral form factor is actually the it's the survival probability for the thermophile double state, right?
Exactly.
And your complexity, I thought, was a little bit more general, that it had the survival probability for not just the thermophile double state, but maybe more than that, right? Isn't that right?
No, yeah, so very good. So here, this I'm just plotting this complexity for the evolution of the thermophile double state. Okay.
Okay.
So that's why the survival amplitude is exactly the amplitude for the spectral form factor. So this example, this plot here is like where I can actually compute these two quantities, and I know they are somehow rooted in the same thing, right? This ratio of partition functions analytically continued. So okay, that's a very good point also. So you see, like somehow this spectral form factor is based only on this phi0, on this return amplitude. Okay.
Right.
But somehow this complexity is not. It's actually, it has the full dynamics in some sense, in a sense that it has phi0, which is the spectral form factor amplitude, but also has higher phi n's. Okay, that are related by some by some differential equations to this phi 0. And
Right.
that's why I was kind of trying to be careful to make, sharp statements, whether the times are the same or not, because it seems like the quantities, like this complexity also uses the spectral form factor, but it computes like also higher, it needs this evolution with this Hamiltonian to have an access to higher coefficients of the higher states in the
Right.
Krylov.
Right. So in some sense, it has more than back time scale. Maybe it has
Yes,
the time
yes,
scales, the evolved
it
states.
has more. It needs more information, not just well. It seems like it needs more fine-grained information, but you can to determine that information, that information is kind of extracted from the spectral form factors, from the moments of the spectral form factor.
Right. Cool. Thanks.
Yeah, thank you.
Thanks a lot for all your patience in answering all our questions. If there are no more questions, maybe we'll let you go. And thanks a lot.
Yeah, thanks a lot. And it was a pleasure to be even virtually at the IFR. I hope I can come at some point in the future in person, so we can.
Yeah, hope to see you here soon.
Okay, well,
Bye.
take care and have a good day. Bye.
Bye.